be telling us something clear about quantum garbled circuits.
Well. Okay. And let's do it. Can you guys see my screen?
Yep. That's all yours.
Hi, everyone. Yeah, it's really great to be in this, well, remotely, sadly, in the workshop. And I have to say, I'm a bit disappointed that I'm the only one who abided by the dress code. I thought we were all going to, wear the shirts, but I guess it's just me. Yeah, so I'm going to tell you a little bit about quantum garbled circuits, and this is joint work with Henry Yuan. So let me start by explaining a notion called randomizing coding, and I'm going to tell you how it relates to garbled circuits. So I'm going to start in the classical setting. So let's take an example, which is just the parity function. So a parity of n bits, just an XOR of these n bits. And let's think about the way that we compute this function. So usually we're going to do it using a tree. So this is n equals 4, but it easily extends. So I'm just going to take sort of a binary XOR tree, and I'm going to be able to compute my parity function. And this naturally has logarithmic depth. Well, it has to because the output depends on all input. And what I want to describe to you is an encoding of this function. So I'm going to use this triangle notation in order to note an encoding. So by encoding, I mean that I'm going to show you a different function, which I claim captures the properties of this parity function in a way that I will describe in a minute. So this function is going to be quite different from parity. In particular, it's going to have multiple output bits. So it's not going to be just a single bit function like parity. And it's going to have more than n input bits. So it's not going to have the same number of input bits, not going to have the same number of output bits, and yet I'm going to claim that it's an encoding of the parity function in an interesting way. So let's see how we define the encoding for this particular function. So what I'm going to do is I'm going to take a random bit, I'm going to sample a random bit for each wire of this XOR tree. And now I'm going to consider the following function. So it takes the original input, and then for each node of this XOR tree, it computes the XOR of all the variables that are adjacent to this node. So we're going to have for the input nodes, we're going to have the X1 XOR R1 and so forth. And then for these intermediate nodes, well, we're going to have again the XOR of all the R's that are adjacent to each one of these nodes. And in the end, we're going to have this R7, which is for this sort of output node. And this is going to be my function. So this is a function that takes, well, it takes X1 to X4. And in addition, it takes R1 to R7, so additional inputs. And it also has 8 output bits. So it outputs all of these individual bits. So it's sort of very different from the original function. And another important property that we want to notice is that the depth of this function is going to be independent of n. So it's actually going to have depth 2, regardless of the original number of inputs, the number of input bits that I had for my parity. So why do I claim that this function actually encodes the original parity function? Well, what I'm going to show is that from the output of this function, we can actually generate the output of the parity function on the respective inputs, and also something along the lines of the opposite also holds. So let's start with a correctness property. So I argue that given the output of the encoding function, so all of these 8 bits, I can compute the original parity. And this is easy to verify. You just XOR all these 8 bits, and you're going to get the original parity of the original 4 bits. So we have correctness here, and correctness holds perfectly. Regardless of what the bits are, which bits are I chose, I'm going to get the original parity that I wanted. The other property is privacy or simulation. And here I want to argue that this new function f hat does not compute much more than, or does not compute anything more than the original parity function. So when I gave you this output, I actually didn't tell you anything about x1 up to x4, except for their parity. And this is formalized using the simulation paradigm, which is very common in cryptography. And where we say, well, if I give you the output, just the XOR of x1 up to x4, then I can sample from the distribution of outputs of f hat that corresponds to these x1 up to x4. So notice that I don't know anything about x1 up to x4, except for the XOR, for the output of f. And yet I managed to sample from the output of f hat. So given an output of f, I can sample from the output space of f hat. So in this case, it's also not hard to see that this holds. actually sort of just take these 8 bits to be random, subject to their XOR being the right value. And this is going to give you a perfect simulation. This is going to be distributed in the exact same manner as the original F hat. So this is a perfect simulation, but you can also think about statistical simulation where you sample from distribution that's statistically close, or even from distribution that's computationally indistinguishable from the real distribution of F hat. Okay, good. So I maybe explained, why I have this other function which I claim captures the properties of F. But why would you want to do this? Why would you want to take a function and encode it by a different function? Well, I mean, this only makes sense if this encoding has favorable properties compared to the original function. So every function is also an encoding of itself, trivially, but I want to come up with encodings that have properties that I can use. So in cryptography, this notion of encoding found multiple uses, which again hinges on the fact that F hat captures the properties of F, but still has very low complexity. In this case, it's going to have low depth or low locality, but you can think about encodings that have other computational properties which are favorable for various tasks that we want to perform. So for example, if we want to perform secure computation of arbitrary functions F, then we could instead reduce it to the task of securely computing randomized encodings of the function that we want to compute. And then we're guaranteed that this gives us the functionality that we need, because from the output of F hats, we can recover the output of F. And also we did not lose anything in terms of privacy, because we did not learn anything from the output of F hat that we couldn't have learned from the output of F. And indeed, low depth complexity comes in very handy when you design secure computation protocols. But randomized encodings have been used for delegating computation, for non-black box constructions of various kinds, and even fairly recently for circuit lower bounds. So this is a very useful notion. So we'd like to sort of study it. So let's take another look at what we have here and look at some additional interesting properties of this randomized encoding of the XOR, of the parity function. So first of all, notice that it has a property that I call decomposability. And this means that in the randomized encoding, each bit of the original input is actually treated separately. So I can actually compute this randomized encoding even when each input bit is held by a different party, and just they all have access to this random string R1 up to R7. And this function can still be computed in this way. And this is, again, sort of a useful property it argues for the simplicity of the randomized encoding compared to the original function. So we have this decomposability property. So the values that depend on the original inputs depend only at most on one original input bit. And then there are some parts that only depends on the randomness and not on any of these input bits. So this is this decomposability property. So I've been talking about randomized encoding, but the title of the paper is Garbled Circuit. So what is a garbled circuit? Well, this term is used for in various ways in cryptographic literature. So let me not give a definition, but rather say that garbled circuits are usually regarded as sort of types of randomized encodings that are computable for a class of circuits, a class of functions, sorry, not just for one function. So for example, you can think about the class of all circuits of a given size. So this is sort of a scheme that allows you to perform encodings for each function in this class. And in addition, usually when you talk about, garbled circuit, it means that the garbling procedure is done in a gate-by-gate manner. So similarly to what you see here. So I sort of do some operation on each and every gate. You can think about this decomposability, but not with respect to the input, but also with respect to the gates of the original circuit, the circuit that I'm trying to encode. So this is what I would call a garbled circuit. But I think the more well-defined term would be randomized encoding. And indeed, it turns out that you can do these garbled circuits or randomized encoding for general circuit classes. There's more than one way of doing it. It's more complicated than what's shown here, but you can think there's sort of a moral similarity in the case that you're sort of trying to encode the functionality of each one of the gates of the circuit using randomness. So this is what we can do classically. And we wanted to try to think whether you can import this notion to the quantum setting and what it actually means. And let me just say that, well, if you look at this sort of decomposable encoding property, it gives you the following sort of strong application, I would say. So let's assume that we have two parties, and each one of them only holds a part of the input. And what they want is to allow a third party to compute a function on both of these inputs, but not to learn anything else other than the output of the function. And using randomizing coding, you can do this with only having shared randomness between these two parties. So in the quantum setting, I think it's not trivially clear how to do this. So if you have a quantum state that is shared between two parties, and you want to allow a third party to learn some function that's computed on the joint state without the two parties communicating between themselves, it's not a trivial task to perform. And therefore, this is one reason we thought it would be interesting to sort of study this notion in the quantum setting. So the first thing that we do is try to define randomizing coding in the quantum setting. And the definition is very similar to what we saw before. So again, we want to encode a function f using a function f hat. And now we're allowing f to be a general quantum function. So it can have unitaries, it can have measurements, tracing outs, introducing new registers, whatever you want. So a general sort of quantum circuit. And we want to encode f using an f hat. And this f hat takes the original input, which is now it's going to be a quantum state. It takes some additional randomness like before. And we also allow it to take some additional quantum states, some additional entanglement. And this is actually only needed if we want to achieve decomposability. Otherwise, you can just generate this by yourself. F hat can just generate E by itself. But for the definition, we want to allow it explicitly. So you take X, you take some randomness, and you take some entanglement. And you, again, want to generate an output from which you can recover. You can decode the original output f of x. And the simulation property, again, is that given f of x, you should be able to sample from the output distribution of f hat. And again, you can think about perfect or statistical or computational notions of simulation. And know that all of this needs to hold also with respect to quantum auxiliary input or side information. So if this input x is entangled with some y, then these properties need to be preserved even when you're, again, even if you're encoding an input x that has side information. So even given the side information, the coding should be correct, and simulation should still hold. Good. So this is the first step to take is the definition. And now once we have the definition, we try to come up with constructions and sort of see how they compare to constructions in the classical setting. So we are able to construct quantum garbled circuits. So these are decomposable quantum randomized encodings that work in a gate-by-gate manner and sort of have these low depth complexity properties. So we actually have the same construction, and we can instantiate it in two ways. One which gives perfect security, so we can have perfect simulation of the randomized encoding, and the other is computational security. So we rely on computational hardness to say that the simulation is indistinguishable from the original encoding. So, well, for perfect security, we don't need to make any computational assumption. And for computational security, we just need a one-way function that is secure against quantum sort of quantum inverters. And in the classical setting, if we try to compare it to classical garbled circuits, well, this is exactly the same. So you can have a construction perfect security without assumptions. And okay, I got some error message. You can still see my screen, I hope. And you can get computational security using one-way functions. Still, so why use one-way functions? Well, you're going to get favorable properties in terms of complexity. So what is the complexity of computing the encoding? So I said that I'm starting with a quantum circuit. So let's assume that the circuit has size S and depth D. And let's see what is the complexity of computing the encoding of this circuit. So in both cases, we can achieve shallow encoding. So the encoding is going to be in the complexity class quantum NC0 with fan out. So here it's actually important as you saw in the example before, the output is going to be typically much bigger than the input, and each input bit needs to sort of affect many outputs. So it's sort of unavoidable, even in the classical setting, to avoid fan out. In the quantum setting, fan out is not as well, straightforward as in the classical setting. And therefore, we need to compute, in order to compute our randomizing coding, we can have constant depth, but we do need to use fan-out gates. So this is where this puts us. Now let's look at, the size of the encoding. So the depth is going to be constant in this model. The size, well, let's start from the computational setting. Here we get sort of the same, essentially the same thing as in the classical setting. So it's just going to be polynomial in the circuit size that we started from, and in this security parameter, which if you know what it is, great. If not, it doesn't matter. So this is the same as what happens in the classical setting. However, in the computational setting, sorry, if I'm allowing to use quantum one-way functions, they're quantum secure one-way functions. If I want perfect security, well, then we have some annoying degradation. So the size of the encoding is going to be polynomial in the size of the circuit, but it's going to be doubly exponential in the depth. And this is in contrast to what happens in the classical setting, where we again get some dependence in the depth, but the dependence is only exponential and not doubly exponential. And it's a bit curious whether this sort of worse dependence is inherent, or whether it's possible to sort of match the parameters with the classical setting. So this is the complexity of the encoding. The decoding is sort of essentially linear in the size of the encoding. So this is also going to be the complexity of decoding and also the complexity of simulation. So this is what we have in terms of encoding. So we might have some blow up, which in the computational setting is only polynomial in the size, but we have sort of shrunk the depth by quite a bit. Another useful property is, well, remember that we talked about decomposability. So each input bit is encoded by itself. So if I own one input bit or qubit, then I only need to look at this sort of random tape and entanglement tape in order to compute the part of the encoding that depends on my input. Now, what if my input bit is classical? Isn't it a bit unfair to ask me to look at this sort of quantum entangled state in order to generate my encoding? Well, our encoding scheme is fair in this sense that if you're a classical, if your bit is classical, then you only need to look at classical randomness in order to encode, in order to compute the part of the encoding that depends on your bit. So there's still going to be some part of the encoding that's quantum. It's actually an interesting open problem to show an encoding which is completely classical. Well, there's also some impossibility results for this. So there's going to be some quantum part for the encoding, but the part that depends on the classical input is going to only be classical. So this is a useful, potentially useful property. So this is one construction that we show in the paper, well, it at least morally matches what is known in the classical world. So we're fairly satisfied, except for this double exponential dependence. We also have another construction in the paper, which I guess is worse in the sense that it doesn't have this shallow encoding. It doesn't sort of the trade-off between complexity is not the same as in this construction that I showed, but the overall structure is simpler, and you do get some beneficial properties from this construction, as was sort of shown in the follow-up work that used this in the context of secure multi-party computation in the quantum setting. So this is another thing that we show in the paper. We also show an application in the context of zero knowledge. So zero knowledge proofs for QMA are sort of very sort of highlighted right now. And there was this very nice work of Broadbent and Grillo that presented the first zero knowledge protocol for QMA, which takes the form of a sigma protocol. So if you don't know what it is, don't worry about it. I'm not going to talk about this application after I'm done with this line. Essentially, a sigma protocol is a 3-message protocol where the verifier message is just random points. And Broadbent and Grillo were the first to show that this is possible for QMA, and it is with sort of a very nice and complicated reduction of a QMA hardness of some problem. And what we show is sort of a fairly simple way to achieve this sort of sigma protocol with some favorable properties. And we do this essentially by taking a classical construction and replacing the classical garbled circuit with a quantum garbled circuit. And this is more or less what you need to do. So we think that this exemplifies the usefulness of this notion in converting things from classical to the quantum setting. For the rest of this talk, I'm going to sort of give you a brief overview of this alternative construction. So we want to try to construct a randomized encoding with some favorable properties that we're going to see for general quantum circuits. So let me be a little more concrete about what is our task. So we want to show this.
Sorry, Zvika, there's a question in the audience.
Oh,
yeah.
If you go back to the previous slide, I actually just had a basic question. So at the top, when you define the correctness property, for instance, are you considering like F, which is a quantum circuit that has a deterministic output, or do you mean that definition to like be about like a distribution of outputs?
Right. So the definition is inherently distributional because, well, F can perform measurements, and it can even take ancilla registers and do Hadamard and measure those things. So it can definitely generate randomness as well. So this definition talks about distributions. So I'm taking a sample from the distribution fx, the simulation. Okay, so the correctness obviously just takes x and computes it takes a sample from f hat and computes a sample from f, and the simulation sort of does the same thing, sort of in reverse. Samples from the correct distribution, gives you a sample from the correct distribution. Does that answer the question? Yeah, it's true that, I mean, in this sense, this is one of the aspects in which the quantum definition requires more care than the classical definition, because the classical definition, you can always say, well, if my function is randomized, and just fix the random string, and then just go on as if it was deterministic. Whereas here you can't play these tricks. All right. So let me go on and talk about the construction. Well, I guess the definition and maybe the statement of the results is kind of important. So if there's other questions, then I'm happy to take them now before we dive in. You can write them in the Q&A also, and we'll take them later. Okay, so I want to construct a simple randomized encoding for any quantum circuit. So for any quantum circuit Q, I want to compute an encoding that has the following form. So I'm going to take my input. I'm perhaps adding some auxiliary register, and then I'm just applying a random Clifford on it. And this is going to be the quantum part of my encoding. In addition, I'm going to compute some classical side information that could depend on, the quantum circuit that I started from, and also the randomness that I used to generate a random Clifford. But this is just going to be some classical information that I'm writing down. So, hopefully this is simple enough for you. So all I need to do is take my input, apply a random Clifford on it. This random Clifford has nothing to do with my quantum circuit. And then I need to sort of write down some calculations and compute some classical side information. So this is what we want to do. And what I want to do here is show sort of a sequence of encodings. So I'm going to use the sort of composability property. So I'm going to start with a general circuit, and then I'm going to encode it by a different circuit, encode by a different circuit, so on, until we get to the point where we get a circuit that has this form. So notice that this is the encoding function. This means that the output of f hat, so if I'm applying f hat, then all I'm getting is this quantum state that is the output here, and this classical information. This is all I need to give you in order for you to be able to decode the output of Q. So I'm going to start with a warm-up. So general quantum circuits is hard. I'm just going to start with a Clifford. So I want the circuit that I want to encode now is some Clifford G. So it takes X and output G applied on X. And let's see how we encode it. So we want to have this sort of random Clifford that's going to be applied on the input. So I'm just going to generate a random Clifford and apply it on my input. And let's take that as a starting point and see what we need to do in order to decode after the fact. So I'm just going to mention, probably most of you know, that for Cliffords are very convenient in the sense that we can efficiently sample a random Clifford, and there also exists a canonical representation. So if I'm giving you a Clifford circuit, you can come up with a canonical representation such that all Cliffords that compute the same function are going to have the same canonical representation. And this is going to be important for us. So we're going to apply a random Clifford. So we start with X and we're going to get Rx. Now I'm going to give you classical side information that will allow you to recover the original Gx. And this I'm going to do just by computing G times R inverse, which is also a Clifford. And I'm going to give you the canonical representation. It's a classical description of the canonical representation of the circuit G times R inverse. I'm going to call this S. And this is going to be our encoding. I mean, this is just has the form that we want. Now, why does it work? For decoding, well, if I'm giving you the output, I'm giving you the output of f hat. So this is Rx and S. I'm just going to multiply S. I'm just going to apply, I guess, the circuit S on the quantum part of the encoding. And I'm going to get Gx, which is what I wanted. Now, if I want to simulate, I want to show you that I didn't give you any additional information. Well, this is again easy to do. Now I'm just going to, so what do I do when I want to simulate? I'm starting with the output. I'm starting with Gx, and I want to simulate the output of the encoding. So I want to simulate something that looks like Rx and an S that looks like this. So I'm just going to do things in the reverse order. I'm going to take S to be a random Clifford, and notice that the marginal of S is just the same as the marginal of a random Clifford. So I'm going to take S to be a random Clifford. And instead of R times X, I'm going to give you S inverse times the input Y that I received. And this is distributed in the exact same way as the original encoding. So this is perfect simulation. This gives you perfect privacy. And notice that in order to perform this process, the simulation, I didn't need to know what the original G was. And this is actually important. If you're allowed to know G, then encoding is trivial. Notice that in order to perform the simulation, I just generated random S and multiplied it by Y. I didn't care if Y came from G1 or G2 or some other, whatever Clifford that you start from. So this is sort of a toy example of the simplest thing that you can do. And this is a little bit takes after some notions in classical randomizing coding. Okay, so this is a warm-up. Cliffords are an easy case. What I'm going to do now is talk about, for some reason I thought I need to end in 3 minutes, but that's not true, right? I have like 18 minutes. Good. So, I hope that was clear. So this is what we did for Cliffords.
But just to answer that, we wanted to save a little question and answer time. That's all.
I'm happy to save everybody the time, but yeah, I'm hoping, but we have time. So if you do have questions, then please do ask or write it down for yourselves, and we'll come back to this in a minute. Good. So now we want to generalize. We want to go beyond Cliffords, and what I'm going to look at is this class of Clifford plus measurement. What is this class? So this is a class of circuits that is defined by two Cliffords, G0 and G1. It takes n plus 1 qubits, X and B. And the first thing that it does is measures the qubit B, gets a classical bit, and then applies, G sub B. So controlled on this classical bit, it either applies G0 or applies G1. So this is, a little bit more than just doing a Clifford, but we know that if you can actually encode this function class, then you can encode everything. And this is because you can apply the sort of magic state transformation of Bravi and Kitaev and represent any quantum circuit using this form. So using layers where each layer looks like this. And we can actually, using the composability property of randomizing coding, we can encode each layer at a time and get the form that we want. So really, the task reduces to the task of giving an encoding for this Clifford plus measurement function class. And again, I want the encoding to have this form. So I'm taking my input, possibly adding some ancilla, applying a random Clifford, and this is going to be the quantum part of your input, of your output, sorry. So you're going to get this sort of quantum value. In addition, you're going to get some classical side information. And from that, you need to be able to recover the output of this original circuit. So let's see how we do this. So again, we're going to do it step by step. I guess in the previous slide we only had one step, but here we're going to have a few. So remember that we're going to try to use the similarity of this class to the class of Cliffords. So before we just had one Clifford. Here we have two Clifford, G0 and G1. But actually notice that regardless of the Clifford that we apply, in the previous slide we did the same thing on X. We just applied a random Clifford on it, regardless of what G was. So let's do that. Let's just take X, apply a random Clifford on it. And now let's think what we need to do in order to recover the value that we wanted. So if I just wanted to encode G0 or just G1, then I had to give you the classical information G0 times our inverse or G1 times our inverse. And this would allow you to sort of recover the output value. So what I'm doing here, I'm going to take the qubit B, I'm going to measure it, and then again, control of the output of the measurement, I'm going to give you one of two classical strings, either the string G0 times our inverse or the string G1 times our inverse. And again, for the same reasons as we had in the warm-up before, if I'm giving you the output of this function, so one of these two classical strings, as well as the output of this, like R times X, then you should be able to recover the proper output, which is sort of G times B applied to the input X. So right now I sort of just use the warm-up as a building block in my construction. So this is kind of cool because, well, we took the complex part of this construction. So you'd think that the part that has to do with the Clifford is going to be complex, and we sort of took care of that. And now this is already in the form that we need, and we only need to take care of this sort of first part. So we're going to try to see how to encode this value. So let's see how to do this. So I'm going to sort of zoom in on it, and this is the circuit that we want to encode. And well, this seems sort of like maybe like a harder task. Well, I said before that the Clifford was hard, but now looking at this, obviously this is the hard part because I need to encode a measurement which is not even a unitary, and I want to encode it using, well, a random Clifford and some classical side information, which again, at least at first glance seems like a harder task. So let's see how to do this. So the first thing I'm going to do is I'm going to sort of run this sort of multiplexer coherently. So first of all, I'm going to sort of use C naughts in order to take B comma 0 and compute from this B comma GB R inverse. And then I'm going to perform the measurement on all of the respective outputs. And this is, well, an identical functionality. So obviously this circuit encodes the previous circuit. And well, now, well, this thing is a Clifford, so this is good. But now I'm sort of left with exactly the hard part, which is doing the measurement. But turns out this is actually not the hard part. And sort of in quantum literature, we know how to handle this. And this is known as the Z-twirl. So in fact, you can replace a measurement in the computational basis by just applying Z to the R for a random R. And again, this is sort of well known that this captures the functionality of the measurement process. But I think this is also something that's insightful in this notion of quantum randomizing coding, because once we have this notion, I can just say to you that a random Z-twirl is just a randomizing coding of the measurement of the measurement operation, and this sort of would tell you what the properties of the Z-twirl are. So, I mean, once we have this notion, we have like a good terminology to sort of address what it means for like this circuit actually captures the essence of the other circuit and so on. So this is sort of a well-known solution to the problem. And indeed, this allows us to encode this function using a Clifford circuit, a random, or rather using, well, a Clifford that is sampled from some distribution, which is defined by the randomness of the sample from some distribution, which is defined by this randomness R, and well, I guess a lot of other things that are called R on this slide. Okay, so we have an encoding in the form of a Clifford. So let's just plug that back in here. And now we see that we have the form that we wanted, right? Now, if you look at the circuit, you take the input and you apply some Clifford on it. It's not a random Clifford because it's like random here and some weird distribution here. But I know how to handle Cliffords. I'm just going to do this group randomizer that I mentioned before, and I'm going to get to the form that I wanted. So I just need to apply random Clifford on everything. And here, well, I'm going to get some classical side information that depends on everything, on G0, G1, all the randomness values that I used. And importantly, I use the fact that this group randomizer actually hides the circuit that I used because I don't want to need to leak these randomness values. Otherwise, well, these encodings are not going to be private. So this is essentially how the encoding works. So I took this, well, I don't know how complicated it looks to you, but somewhat complicated quantum circuit and converted it into this, well, I claim arguably simple form. So it's just a random Clifford and then some classical computation. this classical computation can be pretty complicated. Like who wants to now compute this product and then the canonical representation, so on and so forth. Luckily, since it's all classical computation, we can just use classical randomizing coding and simplify that part away. So, I mean, don't worry about the complexity of the classical parts. We can always just use classical randomizing coding in order to make it shallow and nice and have good properties. So, so I'm arguing that even the classical part is not too bad in this construction. So this is essentially it. This is sort of the simpler construction in our paper. And let me wrap up by sort of talking a little bit more in high level. What would you hope to do with quantum randomizing codings? So I guess you can think about first importing classical applications from the classical world to the quantum world. For example, quantum multi-party computation. This is something that's already done and is fairly sort of straightforward idea to think about. And the other thing which I think could be more interesting is to think about maybe there's quantum applications. So I don't know. I guess in Chinmay's talk we heard about sometimes it's important to consider quantum circuits that are shallow. So if you have a transformation that can transform arbitrary circuits into shallow circuits, I don't know, is this something that can be useful somewhere? The notion of shallowness is not exactly the same as in Chinmay's talk, but just as sort of a conceptual idea. I don't know if there are other places where these things are important. In the classical world, it turned out to be fairly significant and useful. So I guess this bullet is like, I think would be the more interesting one to try to pick up. Yeah, so in the classical, so as I said, the most straightforward thing is to work for secure multi-party computation. I guess I didn't say what secure multi-party computation is. Well, this is the application where multiple parties, each one has their own input, and they want to compute a function on the collection of their inputs. And as I said, well, randomizing codings are useful here, and hopefully, well, evidently, it was used already in follow-up works in order to achieve low round complexity for multi-party computation in the quantum setting. I mentioned this PSM, so let me say what it is. I sort of mentioned it in the beginning when I talked about the motivation. So let me sort of, in the few minutes that I have left, tell you a little bit about PSM, which is private simultaneous messages, and the quantum sort of version of this problem, which is sort of addressed by quantum randomizing coding. So so if you remember the beginning of the talk, I was sort of imagining a quantum state that has two parts. And we have two parties. One party has the first part X, and the other party has the other part Y. These can be arbitrarily entangled, of course. And these are non-communicating parties. They possibly share EPR pairs or shared randomness. And these parties want to sort of produce messages, M1 and M2, which could be quantum, which will allow a third party to compute a function on both of their inputs. And this needs to be done privately in the sense that this computation does not reveal to this third party anything about the inputs X and Y other than the output. And furthermore, you can require, and you can also get that you don't even get information on what is the function that they computed. So this receiver actually manages to compute f of xy, but doesn't know what x was, what y was, or what f was. And again, the classical version of this problem is sort of foundational when talking about secure multi-party computation. You can think about it as sort of first toy example. And in the quantum setting, I didn't know how to. I wouldn't know how to solve it if not by using quantum randomizing coding. So I don't know if. First of all, I think it's interesting by itself that you can do this. Maybe there's other ways. I mean, I wouldn't be surprised if there's some sort of high complexity. So the point in the randomizing codings that we talk about is to also have some efficiency guarantees. So for example, like the length of these messages are going to be like the length of the randomizing coding. So we can have some bound on them. But I don't know if there's some trivial solution that uses arbitrarily long messages and achieves this functionality. I think, I mean, I'd be interested to know, but I wouldn't be surprised. And again, sort of studying this problem with the goal of trying to sort of optimize for different complexity measures turns out to be useful in various settings. except, well, I think also from first principles, it's pretty interesting to think about. Yeah. So the last thing I wanted to talk about was these notions of functional encryption and program obfuscation, which are now sort of take center stage in classical cryptography, also a little bit in quantum cryptography literature. These are sort of more advanced cryptographic notions. I don't want to get into details, but for those of you who know, well, we know that there is a connection between randomized encodings, functional encryption, and obfuscation. Essentially, well, functional encryption and obfuscation, you can think about them as notions of randomized encodings that also have compression of information in one way or another. At least this is one way to think about it. Now, if I had a quantum randomized encoding such that I could encode a quantum circuit with classical input using a classical encoding, then I could sort of push away the problem of sort of doing the compression part to classical functional encryption obfuscation. So if we had, if we could have quantum garbled circuits or quantum randomized encodings where the encoding is classical, like the encoding is completely classical. So if the input is classical and I'm giving you a classical description of the circuit, then the encoding that you get is completely classical. Then you'd get some very interesting consequences when you combine it with classical cryptography, classical cryptographic objects. We know there are some obstacles and impossibilities, so we need to be very careful with what definition of randomized encoding you're using. But again, this is sort of very interesting to understand what can and cannot be achieved, and if it can be achieved, what are the consequences. And well, I'm hoping, guessing that there's going to be more. Thank you.
Thank you, Zvika. Questions?
Actually, I have Zvika, I have a question. So in this, on the quantum side, it's these magic states that play the role to lift these Cliffords to general circuits. So with these parity encodings, what happens on the classical side? How do you go from, is there something similar, or is that more difficult to do on the other side?
So you're saying what's the counterpart of the magic states in the classical setting?
Yeah.
So somehow in the classical setting, well, the problem sort of reduces to just the classical part of, like, it's just like computing the classical part of the encoding. So the part about the magic state part doesn't directly come up, or I guess you're saying what happens when you apply this to a classical, I'm taking a classical circuit, I'm going to represent it using like T-gates or Toffolies and so on. What is the quantum randomized encoding going to look like?
No, sorry. I was sort of drawing an analogy, you know, so Cliffords, maybe they correspond to parities, and, you know, so they are the simple part, but
right.
And then here you lift it using magic states, but on the classical side, when you're going beyond parities, you've got to do something. So does that look more complicated there, or is there some simple gadget that then gets you from parity to everything?
I mean, I think so. There's also the measurement. I mean, there's not just the T-gates, right? I mean, we need to work in order to encode the measurement. This is what makes it difficult. It's not just Clifford's. So you're asking if there's a counterpart in the classical setting. I don't have a direct sort of, yeah, it seems like the difficulty in the classical setting comes up in a sort of different way, which is sort of more similar to how we have our first construction in the paper, which is not what I described in the talk. So here, I guess it's a little more subtle to see the sort of classical analog. I think, again, so what's going to happen is that this magic state transformation is just going to push all the classical computation into what I call the classical part of the encoding. So you're actually going to need to handle it when you're sort of computing the classical part of the encoding.
Okay. It's really nice.
Following up on Umesh's question, what is done for NANDs and other complex functions beyond XOR?
Right. So I mean, so in the classical world, I didn't say, I left you a little bit in the dark. So I don't have that many slides. It's going to be okay to go backwards. Yeah. So so as you notice here, so for each one of these, for each wire, I generate the random bit. So if you're looking at NANDs, you're going to generate something that is longer. So each wire is going to have like a bunch of keys that correspond to what happens when this wire is 0 and what happens when this wire is 1. And sort of similarly to this gadget, but sort of much more complicated, is going to be a gadget that is sort of going to translate if you got some value, some one of these, if the value that you get on the wire is something, then you need to be able to obtain sort of the value that corresponds to the NAND. And this is done essentially by giving you all the sort of different, so in the classical world, it's sort of easy because you can just think about the truth table and encode the truth table of the gate. So if the truth table has, in the case of 2 input gates, it's just going to have sort of 4 lines. Then for each one of these lines, you're going to have a translation that takes sort of the encoding of the input, the incoming wires, and translates them into an encoding of the outgoing wire, which is exactly what happens here. So if you look at, for example, this gate, then if you look at this R1 plus R2 plus R5, then this allows you to take this sort of X1 plus R1, X2 plus R2, and obtain the correct output, which is X1 plus X2, but now randomized by R5. So you need to do the same thing, but for a NAND gate, which is slightly more complicated. But still, you want to sort of preserve this invariant where, if I'm starting from, if I took the randomized version of the value on this wire, on the 2 input wires, and I sort of combine them in the right way, then I obtain the encoded version of the output.
Thank you. We have one Q&A, and maybe this will be the last question. From Vinod. Zvika, can you say more about the Morimae 20 barrier?
Morimae actually showed a barrier towards getting classical. Let me maybe go to the definition. Towards getting a classical encoding, like I said before. So you'd hope that maybe it's possible if my circuit has a classical description and my input is classical, then maybe my encoding can also be classical. However, so long as the output of the circuit can be a quantum state, the ability to simulate actually could violate clonability. So notice that, f of x is a quantum state, so it should be unclonable. And here I'm saying that I can simulate it using a classical value. So if I have a classical encoding, then I should be able to simulate this quantum value using a classical value. Now, classical values can be cloned. So what I can do, or what Morimae does, is say that they could use the simulator, get a classical description of this quantum state that I started from, clone it because it's just classical, and then apply the decoding procedure. And the decoding procedure should still work because, well, this sample is sampled from the correct distribution or from something that is close to the correct distribution. And therefore, what you obtain in the end is cloning of this sort of state that you started from. And this can be a quantum state, even if your circuit is classical and your input is classical. And therefore, this gives you a barrier towards sort of getting some notions, at least getting notions of simulation in the completely classical setting. So this is at least one of the results in the paper, the one that's relevant to what I was saying.
Vinod says thanks, and I would like to join him in also saying thanks to you, Zvika. Thank you very much for a nice talk, and let's give Zvika a hand. Thanks. All right, thank you. So I think this concludes the session for today.
Yeah, just a quick word, Mike. So I just wanted to say that officially